All right. Hi. I'm Alex Gaines, and I'm going to be presenting object diversification with the help of Reordering 2. Some little things we need to get over with in the beginning. I work for Siege Technologies. It's a United States company and does mostly contracts for various alphabet soup agencies. This project, or kind of an overall project that contains this small chunk, was sponsored by IARPA, an IARPA contract, so I have to put that down for the government to not dislike me. So, also, you can totally tell this slide was copy-pasted from another presentation, but another company overview, Siege Technologies, CEO, we got employees, we're all cool and whatnot, you don't really care. Moving on. I'm Alex Gaines. There's my email. Don't spam me. I'll get really mad. I'll probably spam you back. I like binary stuff. I'm sure probably most of you like binary stuff. I've got a few Reordering 2 commits, mostly really gross bugs that no one would ever come across because they're in like very specific scenarios with GDB server. And also, shameless plug, check out WPI CTF. I started it a couple years ago. It's pretty cool. So what is software diversification? Well, we got load time, like ASLR. Everyone knows ASLR, right? But on some embedded systems, ASLR may not be possible or enabled. A lot of IoT devices just don't have position-independent code, so every single address of every function will start with OX40. That's not a good sign. You can have software diversification on compile time, which will go and actually change the source code before it compiles it to generate different binaries. This requires the source code to be there in order to work, and it usually is kind of slow, so not great. There's also binary, which is operating on the binary files themselves, but usually it can't be very advanced or else it'll break things. We're going to be doing binary software diversification, and we may break things, so warning. So why would you want to do software diversification? For defense, mainly to protect against drop attacks. If you can increase the amount of times you have to guess in order to get an address right, that's good. If you make something take 1,000,000 times to guess in order to hack it, someone's probably going to get very bored and try hacking something else in the meantime. So that's good. You can also use to obfuscate things and anti-piracy measures. You can also use offensive, void AV detection, and also obfuscate. So the goal of this project was to make a system to protect kernel modules from ROP attacks primarily through the use of software diversification. This, the Virtue project, the one that was funded by various agencies, was basically a fleet of virtual machines. And every single boot, we wanted the kernel modules that they were loading to be completely different. We want to run the same code, but we want the code and all the offsets and any sort of ROP chains and everything to be different. So that way, it's pretty much impossible to attack using just kind of blind, or using a known binary and generating a attack path off of that. So we'd want to change ROP sets, stack, offset, and layout every single boot of every single VM. Limitations of this has to be fast. We're dealing with virtual machines that are coming up and down every minute. So if it takes a minute to shuffle this thing, it's not really good. It has to be very small. Again, these are virtual machines, and we don't want these VM sizes ballooning out of proportion due to containing a gig of Python libraries. It has to be reliable. This is running on kernel modules, so there's no seg fault and exit. It just kernel panics if you do something wrong. And we're operating on compiled kernel modules, not distributing the source with these VMs. So we want to not require any sort of source. We're dealing with ELF files, and ELF is Linux stuff, basically. You got PE for Windows and Mach-O for Mac. They're pretty much all the same, just have a little bit extra, little differences in between them. The main thing that you need to worry about are symbols and relocations. Symbols are like, if you want to look up the name of function and say, where is this function, it points to that address. Relocation is, I have this function name, and I want you to write the address of it right here. So that's a relocation. If you mess those up, things will also break. So we need to worry about them. Reordering 2 already has ELF code. Sadly, we were already writing the code before we decided to use Reordering 2, so we're going to have to skip over that a little bit. But, all right, easy start. Let's protect these binaries against ROPs and stuff. Well, we can just shuffle the sections of the ELF. Using the GCC flag function sections, or F function sections, it splits every single function into a separate section. Instead of all your code being in .text, it'll be .text .function name. You can also use F data sections, and that every single static variable will be in a different section. It makes a lot of sections. So we can shuffle these sections around, and all we have to do is just update some ELF metadata. That's pretty easy. OpenBSD does something very similar, where it relinks the entirety of libc at every boot. It's kind of slow. I don't like it. One of the reasons why this thing is bad is because there's a limited number of permutations. If you only have 3 functions, there's only 6 ways to order them. 6 guesses is not that bad for a computer to do, and for trying to add years or decades onto a time for it to take an attacker to pwn our system, then 6 guesses is not a lot. We can also add data onto the end of sections. Just add a random number of halt instructions on the end of our text sections. This comes after all the code, so we don't have to worry about messing the code up at all. And it usually changes the offsets between sections. But the offsets inside sections are unchanged. So these are not enough, obviously, or else it would be a very short talk. As you can see here, we have a pretty bad piece of code. I'm sure you've all seen quite worse. But this is in the same section because it's in the same function. We have a leak address right here. Say we get a stack leak or a format string vulnerability or something like that. And then our goal address is right here. That is going to be a fixed size offset no matter how our function order is or how much data we add onto the end of the function. So that's not really good, right? Let's mess that code up. Let's do something to it. We're going to need some help first. We want to do code insertion, kind of hard, and we want to modify the code itself. So we're going to need something to kind of analyze this code. So we're going to use Reordering 2. A few things. It's fast. It's one of our key things that we need, and has low dependencies, no Python. It's also great. It compiles the entire core, all the analysis, all the printing too, down to LibR, and it has some really cool, neat features such as Esil. And I know how to use it, kind of, really not, but I know how to use it more than other reverse engineering architectures and tool sets. So why use LibR, not r2pipe? R2pipe, for those who don't know, is a kind of a text way of interfacing between multiple programming languages and Reordering 2. But we like LibR better because it's fast. Again, we want speed. It's not doing any sort of text API interface that has to go and parse and then reparse and send back at JSON. That's slow. It's also easier to just call functions from a library than it is to interface with text API in C. So we're going to use Reordering 2 to disassemble every single executable section using r_op loops. And basically, r_op function, you set up a r_now struct, give us some information like what file type this is, x86, is it 32-bit, 64-bit, and then you give it the data of the section you want to disassemble, and you keep incrementing this address for every single instruction that you disassemble. It only disassembles one instruction at a time, so you kind of have to keep adding that pointer up as you go through. This gives us a ordered list of this really cool structure and the location. That structure includes the type of instruction, any jump targets it might have, size of the opcode and the actual data it's operating on, the registers being used, memory, blah, 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 blah. Also Esil, which is cool. It's a really big structure. Most of it, if you're doing stuff like this, you won't have to care about, but there are some key things that are pretty cool about it. Esil's also great. Correct me if I'm wrong, but I think it's a valuable strings intermediate language, right? Good. Basically, I was really lazy, and I didn't want to go parse out the registers from that structure, so I just used stir on the Esil. Very easy way to start off doing any sort of automated reverse engineering with binaries in Reordering 2. It's not very good at performance because you're using stir, but whatever. So we came up with the idea of Cruftables. It's a dumb name. I came up with it. So we have our bad function here, and basically we want to do the equivalent to this. Shove data in there, shove code in there that doesn't change the actual outcome of the program, but just changes that offset between the goal and the leaked function. This junk code can be really small, can be really large. We want it to be as random as we can get it. So we need to figure out where to put this Cruftable, and also what it actually is a Cruftable. And then finally, we need to adjust the symbols, relocations, and other metadata in order to accommodate it. So where can we put a Cruftable? Well, we have to put it in between instructions to begin with. We can't cut an instruction in half. This isn't thumb mode. And we also can't put a Cruftable in the concept of a bad zone, which is similar to a basic block, but not quite. It's anywhere between a jump target and the jump instruction that causes that. So anywhere you see an arrow in Reordering 2, bad zone. Bad zones can be a single one, can have overlapping bad zones that can be right next to each other, they can be completely inside each other, you can go backwards, any way you can order a series of jump instructions. So how do we kind of understand this out of the list of RNL ops that we disassembled from? The easiest way is just check the .jump or .fail parts of that structure. If they do not equal -1, it's probably a jump, and then you can just take the bounds of that instruction and any of the locations it jumps to and create a bad zone out of it. What is the data in Cruftable? Well, easy enough. Start off, it's just a jump followed by halts. If someone tried to ROP into anywhere where these halts were, the program would exit in a very detectable manner with a certain signal. It can also be very small. If they're less than 3 bytes, they're just a couple nops. They can also be extremely long. This is a near jump, I think, followed by, I think that's like 800 halts, and that's one of the smaller ones. So they can be very short to very long. After we insert this code into the middle of our section, there's some things that we need to kind of fix up. Every symbol or relocation that comes after the code that we inserted is now going to point to the wrong thing. So we need to kind of push it down. So we got little chunks of code here. We have our original code with the relocation pointing at it. Oh no, we inserted some Cruftables, and relocation is now pointing to the wrong space. So we just add the size of that Cruftable, relock, points to the right space now. Pretty easy. Split Cruftables, mainly just for an obfuscation technique. We can randomly split a single Cruftable into multiple ones, and this can be done recursively. So see, left one, single Cruftable split into 2. And they come right after each other. Here's a split Cruftable that's been split into 3, 2 jumps with halts, and then a knot. So we could use conditional jumps instead of normal jumps to make it a little harder to reverse engineer. But this jump here, if it fails, it's just going to go to the next instruction. So we need to be able to handle that case. Just put another Cruftable there. So no matter where this jump instruction goes, it either goes all the way to the end or goes to the next instruction and then goes all the way to the end. And this can be combined and recursively done with split Cruftables and combine them all in wacky ways to make really gross looking code. Here's an example. It's a small example. Yeah, that kind of looks gross. If you didn't have automated tools to kind of reverse this, it might get a little annoying pretty quickly. All right, so we spent a long time on bad zones saying you couldn't insert there, but I lied. We can. So here's a section of code. Obviously, there's a bunch of bad zones here. We've got all the arrows everywhere. Oh no, we inserted a Cruftable there. How did we do that? We just update the jump offsets. So again, little diagrams. We have a jump, and we're going to insert a Cruftable. Oh no, now that jump is pointing in the wrong spot. Well, we just add the Cruftable size to any jumps it interferes with, and it works again. Pretty simple. So the way we do this is we kind of have a patch system that you keep a list of the modifications to each section that you want to do, and then you process them all at once. And if any single one of them fails, you kind of have to ignore the whole thing. This is very important. It also happens to fix up the symbols and relocations and all that stuff. So in order to modify the jump offsets, we can just take more of that information from the rnal op struct. We can get the start of the instruction plus nop size gives you the start of where the actual offset is. And then we just get the total size, and it's either going to be int 8 or int 32 for a short or a near jump. There's one problem though. Short jumps are only a single byte of offset. It's negative 128 to 127. If we want to put a Cruftable such as 800 bytes in there, we can't do that because we can't make that offset larger. So we have to go and replace that jump with the equivalent that is a near jump, which is a 4-byte offset. You also have to apply this recursively because modifying 2 bytes worth of jump instruction to 6 bytes worth of jump instruction is going to add 4 more bytes into code somewhere. And in a very rare case, that might end up requiring another jump instruction to be bumped. So you have to use this patch system, apply recursively. If any single one of them fail, you ignore the whole thing so you don't mess anything up. There's also one instruction that cannot be bumped, and that is jump of ECX is 0, or hex E3. There's no near jump version of this. So any patches that would result in the bumping of this instruction, we just ignore. So Cruftables can be used to obfuscate things. Here is an example function from an allocator. It's a realloc. And yeah, it looks pretty gross now. It does the exact same code, but if you did not have an automated way of reversing that, it would be pretty annoying. So it's good. You can also do some stack protection stuff, such as stack shims and stack reordering. Stack shims work by inserting a shim into each stack frame. My stacks, high instructions up top, low instructions down. Simple stack frame, let's insert a shim. Pretty easy. And this might protect against out of buffer reads or writes. If they have to guess an offset that now is changing, well, it's more guesses, more times you have to try and hack it, and this quickly escalates into thousands and millions of permutations that we can change this binary up, and that's good. It also may protect against small out-of-bound writes. If you have an off by 1 error and you put a little stack shim in that's more than 1 byte, well, now your off by 1 error is not overwriting anything important, hopefully. We need to align our stack shims to 16 bytes or 8. GCC defaults to 16, and this is because there are some SSE or SIMD instructions that will segfault if they're not aligned to 16 bytes. There's also a performance impact from unaligned memory accesses, it has to do 2. But this is not always required. If you do not have any SSE instructions in that function, or you just want to roll the dice and see what happens, you can try to line it to 1 or 2 or 4. We have to find where allocates and deallocates this stack frame in order to modify it. So the stack frame allocation is in the prologue of the, right at the end of the prologue of the function. Here's main. So you can see it's subtracting 8 from RSP. So that means it's allocating 8 bytes of frame size for this function. You also have to find where it deallocates, and it'll do the opposite. It'll add 8 to RSP and then continue on with the rest of the epilogue. There might be multiple deallocations. Anywhere where you see return in your C code, there might be like at the very end of the function or somewhere in the middle. You need to modify the stack frame there. We also make some assumptions about the stack frames, that there's only 1 per function. It's probably possible to do multiple, but GCC is very kind to us and doesn't. And there's also that the allocations and deallocations are symmetric. There's no subtract 8 to allocate and then add 4 and add 4 to deallocate. That would be also really gross, and thankfully GCC is nice here. So here's some results. Very small function. The original only allocates hex 48 bytes, and then the modified one allocates hex 68 bytes, and also fixes it up at the end. There are some very special cases, but if you want to know more about them, please ask me. We just don't have enough time to get in every single little special case that GCC might do with certain optimization compiler flags. We can also reorder how the stack actually is set up for saved registers. Whenever you have a prologue of a function, it pushes all the callee saved registers onto the stack, and we can kind of mess with those. So we have to reorder in both the prologue and the epilogue, or the multiple epilogues, because there can be more than one per function. Also, you notice that since this is 64-bit, we're only targeting 64-bit, there's no leave instruction used. We just push and pop. So we have to figure out what instructions we can reorder, and there's a whole list of requirements. Basically, the main thing is it has to be, if you're in a prologue, it has to be pushes. If you're in epilogue, it has to be pops. There can be moves. There can be various arithmetic instructions, but nothing that's going to change how program flow goes, so no jumps, no calls, and no memory writes, because that might get into weird territory that we do not quite know of. So we can use, again, rnallup to figure out these conditions for these instructions. The type of the instruction can be used to determine whether it's jump, does it use stack stuff. If it's jumps, you'll have the jump and fail set, Esil as well, and the list of registers. And the list of registers becomes very important pretty soon. I don't think this is terribly important, but I have seen it in one case where you might have the epilogues pop an extra register, and you have to learn to ignore that because it does not exist in the prologue. You basically have to just check that everything is kind of symmetrical. So these are the sections of instructions that we have left. A bunch of pushes, some moves, a move, and a bunch of pops. And the instruction that kind of bounds this, in this case, is the instructions that did the frame deallocation and allocation here, because it's modifying the stack without being a push or pop. We also have to build a dependency list, because even though we want to reorder these instructions, there's some few dependencies that we have to still abide by if we want the program to still execute as it does. Basically, we just look for every instruction before one we're looking at to see if it uses the same registers. In this case, this move instruction uses RBP, so we have to make sure it'll come before the pop RBP when we do shuffle it. Here's an example where it's just some moves after pushes. But the main thing is we keep this dependencies met even after we shuffle it. So even though that the order in which we push is completely different, the move for R13, it came after this push R13, it still comes after push R13. R12 still comes after push R12, even though it's way far away. It just means that we won't accidentally overwrite R12 or overwrite whatever instruction or whatever register we're trying to move it into. We also have to match the order in which we shuffle the prologue and epilogue. So if we shuffle the prologue to be, instead of ABC, to be ACB, we have to make sure that the epilogue matches not CBA, but BCA. This is pretty easy. We just kind of use the prologue as the master and master copy, and we shuffle that one first, and then we try to match with the epilogues. But we do have to keep the instruction dependencies. If there's any sort of way we try to reorder the prologue that we can't physically match with the epilogue because there's weird dependencies going on, we have to ignore it and try again. So here's an example of that. Here's original prologue, modified prologue. Basically, we only shuffled R13 and R12. We swapped them. And the symmetry was that we swapped them in the epilogues as well. I guess I'll do a quick demo. I have here a pretty simple C program that is just an assembler. And I have here a shell script that runs it 100 or runs this makefile 100 times, and in the makefile it does some stuff just to make sure it will run this modification on the executable, and then tests to make sure that the output executable or the original executable and the output still have the same behavior. So we can run it 100 times. Come on, you're faster when you're not in demo. It's very fast, so it's trying to shuffle and test these programs 100 times. So there you go, that was 100 times. So let's compare them, actually. Yeah, that's probably a good function to go to. So the first thing that we notice is these pushes are now different. In the original, we do R15, R14, R13, 12, RBP, etc. In the modified one, now it's R13 first, then RBP, then some other ones. It's still the same registers that are being pushed, they're just being pushed in different order. So if someone's trying to use this as a stack leak, their offset for that saved register might be different. Also, if we look at the, I'm in cursor mode. If we look at the epilogues, it might take a while, I have to scroll through a big Cruftable. You can also notice that big Cruftable that's been inserted. What was that? I think those are confused. I don't know. This will be a while to reverse engineer this if you try to go through this. All right. You can also notice that our epilogues are completely different too. So if you were relying on this epilogue as a part of your ROP chain, well, now the order that it pops things are completely different. It also might have a move thrown in here too if that was part of the original epilogue. So you cannot rely on these ROP gadgets anymore either. I think also, do we have... it has a stack frame, but we did not apply a stack chain to this just because it's a random chance that we do. You also notice that in my makefile, the name of the shuffler is .self-hosting. So the actual shuffler itself is originally ran on itself to create a shuffled version of the shuffler. So that's one of our tests that we use to make sure that it works on special cases. Because if you're just running something on like little toy test programs, they're only 100 lines each, you're not going to get into crazy weird issues that if you have certain compiler options enabled, then you have a function with like a billion arguments that starts pushing them on a stack, and you use switch tables at the same time, causes some weird issues. So training or testing this on itself is very useful. I think that's pretty much it for my demo, unless you guys want to see anything in particular. No? Oh God, that would take forever. So you'll notice that it's shuffling the objects, and in kernel modules that's okay because when you load a kernel module, it's directly linking against that object. In binaries, you still have to link against them, but since our goal was to do kernel modules, that's fine. So Firefox, I'd need to like try to get to link and figure out their build system. I was trying to actually figure out how to do this against Reordering 2 itself last night, but I couldn't figure out your build system, sorry. A bunch of future things that we want to do, such as porting it, full binary support, you don't have to link it again, different file types, cool stuff. It'd be really cool to make it so that you can have it as a kernel module so that as you're loading the program, it's actually shuffling it instead of like a two-stage process. So that'd be pretty cool. Special thanks to my boss, my coworker, anyone here who's ever committed code to R2 because you've probably fixed some of my issues and made my life easier. And thanks to also my company for sending me here. And you guys have any questions?
Any question?
Why me first? Where can I get it?
So the source code is not online yet, but we are planning to put it online hopefully within the next week. Basically, I just got to pester my boss enough. So
Where are you living so I can knock on your door if you don't open source it?
Yeah, that's true. You can email me in a week if it's not up there. So, oh, if you have any questions, you can also email me if you don't want to yell them here.
Oh, one.
Yeah, it's nice, cool idea. Does it rely on specific, or does it support all the GCC compiler optimizations like link time optimization or stuff like this?
I'm not sure about link time optimization, but a lot of my test cases I've been running with through O0 through OFast. There's some special cases we had to program in for like sibling calls, tail call optimization, weird things where we use RBP as a local variable instead of a stack-based thing for referencing stack arguments. So there's a lot of special cases that we had to program in to support the more advanced GCC things.
Okay, thanks.
More questions? Yep.
Can you use this for resizing sections for adding like arbitrary patches into the code, or is it only for adding like the knob slides?
Yeah, so one thing I might want to do in the future is kind of make like a plugin for Reordering that just lets you, for a better word, yeet code in there. So it automatically fix up all the sections, all the relocations, all the symbols, do the jump stuff as well, and then tell you if you can't physically insert it there because there's a JECXZ. So in the future, yes.
Cool. Any other question? Yeah.
Really cool tool, by the way, and I'm seriously excited about you open sourcing it later.
Oh, thanks.
But just one question: did you use R2 for the editing of the assembly itself, or did you just go pure C++ and modify the bytes itself?
I think at the moment is pure C. There was one special case where it started using, I was really lazy and I didn't want to have to figure out how to like modify an instruction to convert it from using RBP to RSP. And so I just stir copied the instruction and replaced RSP with RBP and then used Reordering to reassemble it in place. That didn't really work, but I think in the future, if we do port it to like a plugin, we'll use Reordering for doing these modifications.
Thank you.
More questions? Yeah.
Is this running in production?
Yes, it is actually. It is running. If you look up the Virtue project under IARPA, it's there's some pretty cool places it might be being run soon, and it's already being run in production in some cool places too. Can't really disclose much more than that, but stay tuned. It's cool.
More questions? Nope. Yeah. No one.
How does it, well, when does it determine that enough shuffling and enough Cruftables are enough?
It's completely random at this point. So I think it just keeps looping until a random count or random percentage is less than 10% or less than 5%. That's tunable. And then the size of the Cruftable and where it puts it in also is random as well. So probability, I guess.
And, well,
Oh, and you can also keep rerunning it. So if you see here, I have test suite 2 and test suite 3. Test suite 3 was I ran the shuffler on the already shuffled version, so it made like a super shuffled version that is absolutely disgusting to look at. Do not under any circumstances try to reverse this thing. So you can tune it to be as gross as you want it to be.
and have you tested how the performance impacts?
So I don't think I have any concrete numbers with me, but the performance impact is low enough so that we didn't have to do any testing. Yeah. And that was being tested on kernel modules that were being used for like syscall hooking and stuff, so they'd be running quite often. So I assume it would have some impact with like the cache and the jump predictor and that sort of stuff in the CPU, but it's not running any more code than it already would be. It's just kind of jumping around a little bit.
Another question?
can only ask one question? Now I'm going to ask a second one. Is it working? Like, did you try to give it to some exploit writer, for example?
Oh, I have not tested it on anything that is not output by GCC.
No, I mean, is it working against exploits?
Oh, yes. I do have some examples. So here's an example stack break, I guess. Original code, it will segfault. Oh, did I not write that right? I did not run that right. Original code will segfault there. And this is showing off stack shims, by the way. Modified code will not segfault. Yay, it managed to get past that. So that's just an example of how stack shims may protect you against small overflows. I think I have a big one for a big ROP chain as well. But this ROP chain is so complex that like it might just break on its own. So hopefully this will work. So original code, you get calc, yay. Modified code, let me check the make file first. No, I need to shuffle this as well. Yeah. So modified code doesn't work. And that's just because it's changing the ROP offset, so any ROP chain will basically break at that point. If you can, like when this goes open source, if you can like, it'd be really cool if you find ways to break it or find ways to make things that are still exploitable after it's been shuffled. That'd be really cool too.
It sounds like it would be really useful on systems that don't have ASLR or anything like that, like embedded systems that are statically linked.
Yeah, so one thing that you could use this for, I just got an idea for right now as you mentioned it, is let's say you're shipping out an IoT device that for some reason is statically linked and has no ASLR because IoT.
Happens.
If every single firmware you push onto that device had a slightly different version of all the binaries, pretty good.
Exactly what I was thinking about.
Yeah.
So you release all the devices with different binaries, different offsets, different addresses.
Yeah. You can also use it for anti-piracy measures. Like, let's say you have a game, and every single version of the game you distribute on Steam or whatever, Steam probably doesn't support this, but you give a different version of that binary. If someone cracks it and then uploads it somewhere, you might be able to figure out who was the original cracker just based on kind of a signature of how that binary was modified. So there's plenty of use cases for this thing.
All right, thanks.
Nice. Last question. Well, I have 3 more questions there.
Really cool tool, by the way. But is there a way you can actually shift back or have some sort of mapping file to figure out what the original was? Because I imagine this is probably going to be pretty painful in production if something does happen, right?
Not at the moment. It's mostly like a prototype that works at this stage. But again, once it goes open source, if you want to make something that can like save that information of how to get the original seed back from it, that would be excellent. So not at the moment, but probably possible.
Very cool.
Okay, thank you.
Again, if you have any extra questions or want to bug me about releasing the source code, feel free to email me. So, right there.